Okay, so magnetism. These are pretty pictures. One picture is an actual photograph, and one is a picture showing how the Earth is kind of like a magnet. So let's start with the photograph. What is that? Aurora borealis, or more commonly called northern lights. Northern lights are lights you see in the sky in the northern hemisphere. What if it occurred in the southern hemisphere? Okay, southern lights or aurora. Instead of borealis for north, is australis for south. So you have northern lights and southern lights, aurora borealis or northern lights. Since we're in the northern hemisphere, that's all we're going to see up here. But if you live, let's say down in Australia or, Chile, Argentina, something, you would be seeing the southern lights. So those southern lights or northern lights are caused in part because of the Earth's magnetic fields. So that's why this picture is here, because it's something that allows us to see a visual effect of the Earth's magnetic field. Here is a picture depicting what the Earth's magnetic field is kind of like. Now let's just talk about magnets. What's the basic thing that you learned about magnets when you were a young child? The what? Okay, magnets stick together. So I have some magnets here. Magnets. They stick together. Take it apart, put it back together. These are pretty strong magnets, so I can do cool little magic tricks. Like, I don't know if you, there's something on there. If you watch these TV shows of magic tricks where people, sit here and they move something on the table and everybody's like, ooh, they're doing some magic? No, they're doing exactly what I'm doing. They have a magnet underneath, a magnet on top, and because of the force, they're attracting. Now if I take it, put it here, I was able to pick it up without touching it. Definitely a force that acts over a distance. Another thing you learn about magnets real quickly is that you have magnets that will attract and repel. So, let me grab one of these. Here's a compass. The compass has two vanes. One is supposed to point north and one is supposed to point south. The one that points north are called north-seeking. The one that points south are called south-seeking. And if you look at this, it has N and S marked. What direction is north? Edward, what direction is north? I'm asking you because I know you live in this vicinity. That direction. Brittany, what direction is north on this compass? Oh no, it's pointing the wrong direction. Well, if I go like this and make it move another, comes back. Something's wrong with my compass, right? Well, let's check out some more things with the compass. Here is a magnet that I'm going to trust the N is marked right. Bring it up here, and hey, the N's are coming together. Turn around to S, hey, now the S's are coming together. There is definitely something wrong with my compass. But we have two different kinds. Just like with charge, we have two different kinds of magnetic charge. Now, because there's two different kinds of magnetic charge, and one side seeks the north, we have come to calling them north and south. But it turns out that opposites attract. Just like with charge, opposites attracted, positive attracted negative. With magnets, opposites attract, so north is attracted to south. And now we come to a real oddity, because the north of a magnet is the north-seeking side. So it's going to point toward the north pole of the Earth. But it also is attracted toward the south magnetic pole because it's attracted to the opposite pole. So if it's attracted to the Earth's north pole, but to a south magnetic pole, what does that tell you about the magnetic pole at the north pole? It's south. So basically, we as humanity, didn't understand really what was going on with magnets when they decided to call it north and south. And by their definitions of the north and south poles, you end up with the Earth's north pole as a south magnetic pole, and the Earth's south pole is a north magnetic pole. So the Earth, the picture here is showing the Earth as if it's a bar magnet. And now we have all of these lines. What would those lines be? Magnetic fields. It's a force field. We've just finished talking about electric field lines that were force fields. And those electric field lines were used to calculate the force on a particle. Likewise, we're going to use magnetic field lines to calculate forces on particles. So it has the same purpose. Now, the magnetic fields we'll see is a more complicated situation. We will, in this class, never get to the point of talking about the force between two magnets. It will always be the force on a particle due to a magnetic field. Magnetic field lines. I'm sure I have this coming up. I've got slides with words galore. I cut out like 5 slides because they just, with so many words, it would bore everyone, I thought. So I say the words and look at a few pictures instead. These magnetic field lines are different than electric field lines. What do you see about these field lines that are different? The what? Okay, that is an important thing. Magnetic field lines go into the South Pole. And then they go through the magnet and come out of the North Pole. So magnetic field lines go into south and come out of north. It's an important observation. What else do you see that's different than electric charge, electric field lines? Lauren? Okay, that's what I was looking for. Magnetic field lines always form loops. Electric field lines started or ended at a charge. Magnetic field lines don't have a starting or ending point. They do loops, closed loops. So all of those magnetic field lines go into the south, continue through, and come out the north. As far as we know, there is no such thing as a magnetic monopole. A magnetic monopole would be just a north with no south. We have lots of examples of just an electric monopole, just a positive charge with no negative, or just a negative charge with no positive. But as far as we know, no magnetic monopoles exist. Now, people have done research. In theory, they could exist. Guth, I can't remember Guth's first name, did some calculations, and he determined that during the Big Bang, there would have been enough energy to conceivably make as many as 7 magnetic monopoles. So they could exist. There could be 7 in the universe. We wouldn't expect to find them if there were only 7 in the universe. And of course, chances are none exist. So, like, if it comes up on the MCAT, just say magnetic monopoles don't exist. Right? They're certainly not known to exist and are unlikely to exist. Things that are the same about magnetic field lines and electric field lines. What do you see that's the same about magnetic field to what you saw with electric field? There's something that electric field lines have that equipotential lines didn't have. What did the electric field lines have that equipotential lines didn't have? That's about as much leading as I can do on this topic. Direction. Magnetic field lines, like electric field lines, like gravitational field lines, have a direction to them. So there's direction to these, and that direction is going to have something to do with the force. Another thing that's like electric field lines is that you can determine the relative strength of the magnetic field by how close the lines are together. So here, where the lines are relatively close together, how do you suppose the magnetic field there compares to the magnetic field out here where the lines are farther apart? Stronger where they're closer, just like with electric field lines. So where you go into the poles, they're really close together, very strong. Inside the magnet, really close together, very strong. So permanent magnets, such as I pretend this is, have magnetic field lines that, well, look kind of like you see in the picture. The picture on the left is a picture made by taking a bar magnet like this, putting it down, putting a piece of paper over it, actually giving appropriate support so the paper is not wavy, and then just spreading iron over it. Iron is strongly magnetic. And because it's strongly magnetic, the little grains of iron will align on the magnetic field lines. And so you can look at that picture and you can see the direction the magnetic field lines are pointing. And then the picture on the right is just taking that and looking at the line directions. So you can definitely see that you have the two poles, the two places where the lines are essentially coming out radially in this picture. We're a little bit above. You don't see the three-dimensionality to it. And yeah, that's what a bar magnet's like. We've already talked about the, I forget to get these things pushed back into shape. We've already talked about the magnetic field lines coming out of the north and going into the south and never having a start or an end. The symbol for magnetic field is a B. Honestly, I do not know why it's a B. It's a B, it's a vector, so we have bold B or B with an arrow over it. Here I have a bold B with an arrow over it just to cover all the bases. And the units are Teslas. Now, there are other units that you can use for magnetic field. The other one that's common is the Gauss, G-A-U-S-S. And 10 to the fourth Gauss is equal to 1 Tesla. Let's see, a Gauss, I got to remember now. I think it's a G-A. I never use Gauss, so I don't know if it's a G or a G-A. I don't know. I feel stupid not knowing the Gauss. That shows you how much I use them. So the Tesla is the standard unit. And we will work out a little bit later what the unit of Tesla turns out to be in the base units. It obviously is going to have something to do with charge or current and mass and time. Yeah, talked about that. The no magnetic monopoles is illustrated by this. If you take a bar magnet and you break it in half, one might think, hey, I have a bar magnet that has one half is south and one half is north, so I break it in half, I'll have the south half and the north half. But if you break it in half, you have each one has a north and a south on it. And if you break that in half, each one has north and south, and you keep going, and you'll always have that occurring. You'll never have just a north or just a south. All the way down to you get to the individual atom. And the individual atom will have a north and a south to it. You get down to the electron. The electron has a magnetic moment. It behaves like a bar magnet with a north and a south. We talk about the electron's magnetic effects all the stinking time, but you probably don't even know it. So I'm going to ask, does anybody know what the common term is for talking about the magnetic orientation of an electron? I'll guarantee you all know the term. Did you say something? It's the spin. The spin of an electron is a measurement of its magnetic moment. Electrons have an intrinsic magnetic moment. They behave like magnets because God made them that way. Right? Intrinsic means it's just part of how it is. we don't have a real understanding of what would make them magnetic, just like we don't have an understanding of what makes mass. Right? We say, the Higgs field gives you, a lot of the apparent mass of the stuff we have around us. If you look at the mass of, an up, up, down, or up, down, down, you add those together and you get far less than the mass of a proton or a neutron because of the Higgs field. But we don't really know what causes the magnetism of an electron. It was thought that the electron having charge must be spinning. That's what gives it its magnetic moment. Because you can make a dynamo, you can have charge going around the circle, such as what makes the Earth's magnetic field. We have in the Earth conducting material in the core. We believe there's a molten core of iron and nickel, and that molten stuff is swirling around and it's creating the Earth's magnetic field. So scientists back in the 1930s, I believe it was, they noticed that electrons behave differently when you put them in magnetic fields, deduced they have a magnetic moment, and said, well, it must be because the electron is spinning, and that's why we have the term spin. But further evaluation while we don't know the size of an electron, we can say it's got to be smaller than me. And if the electron is smaller than the size that we have for its maximum size, there's no way it can spin fast enough to create its magnetic moment. So it has to be intrinsic. The spin has nothing to do with spinning. A little disappointing, isn't it? Because you always think about that kind of like a top spinning. But it has nothing to do with it actually rotating. And spin up and spin down, if you put an electron in a magnetic field, it will either try to align with the magnetic field or try to anti-align with it. But then quantum physics plays a little trick on us. It can't align. Right? We have this here that's aligned with the magnetic field. Well, the electron can't do that. It can only be partially aligned or partially anti-aligned. It's kind of crazy. Quantum physics will do that to you. Something to look forward to. Well, he doesn't sound excited. Okay, I've already talked about this. I already talked about this too. I've talked about a lot of this stuff. It is important to realize there's not really a magnet in the Earth. Right? That's something we talk about to understand it better. What did I say creates the Earth's magnetic field? It's what? Molten iron and nickel. It's the molten core. For any of you old school WoW players who played World of Warcraft, 10 years ago, it used to be an epic 40-man raid to go do the molten core. Yes, I cheered profusely the first time we took down the end boss, I think it was Ragnaros or something like that, in the molten core. Well, the Earth has a molten core. It has a solid core inside, but that molten core is swirling around and gives us our magnetic field. Now, when you think about its swirling material in there making our magnetic field, it doesn't seem quite as, well, this is silly to say, but as solid as it would if we had a fixed magnet in there. And the fact is, it's not. We have the sun, a much bigger object, that is rotating, and the sun has a very, very strong magnetic field. And the sun's magnetic field actually flips. Every, I think it's approximately 13 years, it flips. So what was north is south, and what was south is north. And a few cycles back, they were making some very careful measurements of the magnetic field on the sun, and they saw that one pole flipped and the other didn't. So for a period of less than a month, the sun had, I believe it was two north poles, two north magnetic poles. How does that work in the context of what I've already told you today? Yeah, that's what it can't be, I said.
Because it has multiple small orientations inside.
That's right. It's basically like you can take two magnets and hold them so this one has north up and hold another one. So this one has north down. That's basically what you have going on. But the sun's magnetic field flips. So can the Earth's magnetic field flip? Has it flipped in your lifetime? No. No, but we can use what's called paleomagnetism to study the ancient historic magnetic fields of the Earth. How do they do this? Well, you know that we've already said magnets create a magnetic field. I may or may not have made it clear that magnets try to align with the magnetic field so that the magnetic field lines go into the south and come out of the north. So if I put this magnet in the Earth's magnetic field, it's aligning, so the magnetic field lines are going with it. That's what makes it rotate. So if I have molten rock come out of the Earth, it contains iron. That iron will align with the Earth's magnetic field. But then when it freezes, it's kind of stuck. And so seafloors have permanent magnetic properties because of the molten metals aligning with the Earth's magnetic field when they froze. And so scientists have gone over the seafloor and carefully measured the orientation and the strength of the magnetic field that's frozen into the ocean floor, and they find the magnetic fields have indeed switched. And it switches on average, I think it's like once about every 200,000 years, somewhere in that ballpark. So of course that's typically no one's going to live through 2 switches. How long has it been since the last one? In the ballpark of 1 million years. So we're way, way overdue for the Earth's magnetic fields to switch. Hence the movies that came out, 5, 6 years ago, where you had things, the core, right? You guys seen those movies? Hollywood is such copycat. There are like 2 movies, the same idea that came out at the same time. They depict things like the Earth's magnetic field is changing. What are we going to do? Ah! And it's great because they have scenes like the birds go crazy and they start flying into everything and making, flying into buildings and flying into people, and everybody seeking refuge from the birds. Does that make any sense? At some level it does, because we know that the birds actually use magnetic fields for navigation. And so if the Earth's magnetic field suddenly go haywire, that aspect of their navigation is going to go haywire. But that wouldn't necessarily make them just get angry and fly into people as swarms and stuff. That seemed a little extreme for, I guess that was the beginning of the whole Angry Bird movement, right? Magnetic fields just screwed up. There are other things that use magnets. I think it's lobsters use, this is not magnets, but it's a totally cool experiment. They use like grains of sand and have little things with the grains of sand, and they can tell what direction is down just by the direction the sand hangs. And so scientists did experiments where they replaced those grains of sand with little beads of iron. And then they put a magnet above them. And what do you think the lobsters did? They flipped over on their backs because their little grains of iron told them that up was down. Okay, but that's not part of our physics. It's just fun things that scientists do. Okay, first clicker question. Which magnetic pole is the Earth's north geographic pole, or is at the north geographic pole? Okay. Brittany, James, Noah. Brittany, James. Brittany. Can't log in? Okay. The answers are coming hard and heavy here. They're changing over time. Oh, Brittany's in. Now we can stop. Oh, goodness. This is such a nuisance. We had, I believe it was 10 here. it was something like 6 here. And yeah, the software kind of didn't preserve it. I'm only going to stick with those two because both of those answers are fully defendable. They're both correct in their way. At this moment in time, the correct answer is B. But it varies with time over a very large scale. Don't expect it to change in your lifetime. But it does vary with time. And in fact, the Earth's north magnetic pole, well, let's stay with south magnetic pole, so we're talking about the north, it wanders as much as 60 miles in a day. Why? Because you have fluid dynamics that's causing that magnetic field. You also have lots of shifts in the Earth's magnetic field because of the sun. You have daily shifts in the magnetic field, seasonal shifts in the magnetic field. So you have the diurnal and the annual shifts. Yeah.
So could like this shift affect like someone like lost in the forest who has a compass pointing north?
Yes. In fact, it's very well mapped. If you are a pilot, you have maps that tell you about the magnetic deviations. And those will tell you about the local deviations, the average at any location. And some places, the compass points about 20 degrees away from true north. And so it varies. And so a pilot has to know, I'm in this region, I have to correct my compass for the deviation in this region. Now, that's not taking into effect the diurnal changes, the changes every day. But those are going to be a smaller effect. Okay, what kind of materials are magnetic? Well, we call them ferromagnetic, and ferro is a hot tip. What? Yes, I heard somebody say iron. Iron is, I always say ferrous, but I'm sure that's the wrong form. I'm not as good at Latin as I should be. But iron has a strong magnetic property, and thus we call things with strong magnetism ferromagnetic. And so ferromagnetic materials include nickel, cobalt, and chromium dioxide in addition to the iron. Now, I'm sure there are more besides these. These are the ones that are well known. So when I was a child, we had these little things that were magic that we called cassette tapes. And you could record music off the radio and you could play it later. And it was amazing. And when you went to buy those tapes, they had things on them saying like CHR2. I think that would be one of the things they said. And I was like, I wonder what that means. Well, that would be that it was using chromium in, chromium-2 as its magnetic material. Because what you had on this tape was a piece of, what is it? Cellulose? Not cellulite, that would be funnier. And on top of that, you have a gel. And in that gel, you have little magnetic materials. And then you just pass a magnet over it, and those magnetic materials align with the magnet. And your data is stored by what direction are those little magnetic materials aligned. That's how magnetic tape works. Just aligning the magnetic materials. Now that gel, it's kind of important that it kind of holds it in the same position. Over time, they're going to deviate a little, and so you have degradation of your recording quality because they don't maintain their magnetic orientations very well. So that's the kind of media we used for our sound back in the day. Different kinds of magnetism. I'm going to come back to that actually. Let's see. Yeah, I got time. You have paramagnetic substances. Paramagnetic just means it's a much weaker form of magnetism. So magnetic materials, opposites attract strongly if it's ferromagnetic. Weakly if it's paramagnetic. And then there's the bizarre one, diamagnetic. And diametrically opposed, that's what diamagnetism. Diamagnetism is repulsion. So magnetic fields repel instead of attract. And every material has this diamagnetism. But if it's paramagnetic, even that weak paramagnetism is stronger than the diamagnetism. And if it's ferromagnetic, well, that's way stronger. But this video, oh, shoot. Okay, you can go do it on your own time. It's actually not that exciting, but it's just showing the frog levitating. The frog has water. The water is diamagnetic. You put water in a strong enough magnetic field and you'll make it levitate. And so the frog being largely water, you put the frog in a strong enough magnetic field and you make it levitate. Now, of course, people did it first with other things, right? You know, strawberries. Doesn't damage the strawberry. Frog. Doesn't damage the frog. You'll be glad to know. The frog just floats around. If you watch the video, you'll see it randomly kicking a little. But it's just floating in the magnetic field. Totally cool. What was that?
Did it think it was in water? Is that what it's thinking?
I think it was just because it was floating around a little disoriented, trying to figure out, how to get oriented. So all materials, including liquids and gases, are either ferromagnetic, paramagnetic, or diamagnetic. Ferromagnetic, strong magnetism. Paramagnetic, weak magnetism. Diamagnetic, really weak, opposite magnetism. Now getting back to how magnetic materials really work. It comes down to the atomic level. Some materials are magnetic because the atoms are made out of. Some are not because the atoms are made out of. Now when I say they're magnetic, I'm talking ferromagnetic. And so if you have a ferromagnetic material like iron, then you have in the material little domains, little regions where all the magnetic fields of the atoms are lined up together. And those domains are each one acting like a bar magnet. And in a normal material like normal iron, you're going to go to the lowest entropy state. Those domains tend to be just randomly oriented in all directions. But if you put it in a magnetic field, they'll kind of realign. And so you put a magnetic field and suddenly that iron will behave like a magnet. Take it out of the magnetic field and over time it's going to lose the alignment. So you can make a magnet just by putting a strong magnetic field if it's ferromagnetic material, if it's something the magnets are attracted to. So here is my magnet maker. Now you saw that compass was just plain wrong. Why is it plain wrong? Because I messed with it with my little magnet maker. So I'm going to take this, here's the north side. To avoid any kind of confusion, I put on here, put N in here. It has it marked S and N, and people get really confused, including me, with their notation, so I just made my own. So I put it in here. I have these pieces of metal. These are pieces of iron that are going to then make the magnetic field so it stays basically in the metal because it's much stronger because of everything aligning. And I make a loop. I press the button. And so now I'm going to take it and put my compass back together. And it comes around. So now the north is going that direction. I fixed it. Actually, God, I was able to fix my compass. And so you can take things and realign the magnets, realigning those domains by putting in a really strong external magnetic field. Now, some things we call them hard, magnetically hard. If it's magnetically hard, the orientations are frozen pretty good. It's hard to change them. Magnetically soft, they change fairly easily. That's fairly magnetically soft because I can easily change the magnetic field from going one direction to the other. Likewise, these are magnetically soft. I can change the orientation just by putting it in there and pressing a button. So that's just making a strong magnetic field and allows me to make my orientations. It's very cool. What if you want to get a good permanent magnet that's something hard? Let's take these babies here. These are very strong magnets. They're strong enough that I keep them separated by paper, because if I don't keep them separated by paper, I have a very hard time taking them apart. So these are, there we go. Now they're, so let's go to Lauren. Can you take them apart? It's very hard. No one is going to just yank them apart. To get them apart, you have to slide them against each other to get them so their magnetic fields aren't perfectly aligned, that it's a weaker attraction. And then, a little careful work. Yay! And so that's why I have 3 of them here. One there, piece of paper, one there. I don't have to worry about it being hard to take them apart. You can also do cool things. Okay, so this is attracted like this. Same orientation, flip this over. Now it's going to be repelled, right? So if I bring it down, watch what happens. You got to watch closely. What happened? It flipped over and then came up. Why did it flip over? Because the force was so strong, I was off to the side a little bit. It's pulling one side up and pushing the other side down. So just like a dipole, it flipped around and then the attraction took over. You can do lots of cool things. Now, these here are also the neodymium magnets. These were a poor purchase because trying to take them apart, you end up breaking them half the time. Because if you get them apart a little bit and you let go, they snap together and they break. They're kind of fragile magnets. In my office, I have 2 bigger magnets. Isn't there a group that's working with magnets for lab? So you'll want to talk to me about what magnets I have and what you need when you get to that. Here's a magnet. How does this magnet work? First of all, can anybody guess where this came from? It's a speaker magnet, that's it. It came from a speaker. If you were to have it in your hand like I do, you'd see there's still some felt here from the speaker cone. So with this speaker magnet, I'll bring it up here. It's pushing the north down. What does that tell you? Since this is north seeking, my north pole must be down here and the south pole up here. And so it's, yeah. So this has its poles. This one here is south now, the top is north. It's how this one has its magnetic fields made. So you have different styles of magnets depending on your goal for the magnet. What in the world? Well, I found one of my little balls. Get back in there. Magnets are fun to play with. Let's get back to the lecture for the last 7 minutes here. If you want to make a permanent magnet that's a hard material, which is where I started when I started playing with the magnets, you take a magnetic material and you raise it to the Curie temperature. The Curie temperature is the temperature below the freezing point, so it's still solid, where the magnetic domains can freely rotate. And so for iron, you'd have to raise it above 770 degrees Celsius. Then you put a strong magnetic field and cool it down, and you'll lock in the magnetic orientation. So that's actually how a strong permanent magnet is made with a material that's not magnetically soft. So, yeah. Not the last thing, but another cool thing. Another very cool thing. We like to make strong magnets, right? It's just more fun. And while magnetic materials can make strong magnets, it's a lot easier to make a strong magnet by making a coil of wire. And we'll learn this coming up in the next week. A coil of wire will make a strong magnetic field. But then if I put iron in there, the iron magnetic domains will orient with the external magnetic field that we're creating with the coil. And that will increase the magnetic field by hundreds or even thousands of times. So if I make an electromagnet and then put an iron core in there, it'll really boost the magnetic field. So next week I'll be doing a demonstration and showing you the difference of having an iron core and not having an iron core. Now, everything that we've talked about so far today has just been knowledge about magnetic fields. No solvable math problems, just understanding the concepts. We will get solvable math problems, maybe a little bit today, but probably not until Wednesday. Wait, Wednesday? Today's Wednesday, isn't it? Friday. Took out the recycles today. That's Thursday. I got confused. I have a picture here of another application of magnetism. This is a computer hard drive. The hard drive consists of a set of platters. Those platters are just discs. And on top of those discs, you have a gel. And in that gel, you have magnetic materials. The hard drive in your computer is the same technology as that old cassette tape. What's different about the hard drive versus the cassette tape is the size of things. They can store information much more tightly on that hard drive than they can on your cassette tape. That hard drive spins rapidly so that you can check different places on the disk easily, whereas with the cassette tape, you had to roll a whole lot of tape to get to where you wanted. So they're just a lot more efficient than cassette tapes. Of course, these days we're moving to solid state hard drives. And so the SSD is a different technology. It makes me sad when we move away from our classic examples. Okay, second clicker question. What kind of magnetism is always present in materials? You don't notice it unless the other two are absent, but what kind is always present? Oh, yes. Polling is open now. And the answers come flying in. Logging in again. Okay. The last second, two people changed. The kind that is always present, those two people changed from right to wrong, is the one that we had a majority, diamagnetism. Diamagnetism is always present, but you're not going to observe it unless you don't have the other two because it's much weaker. Which kind of magnetism is the strongest? That was quick, Lauren. Okay. Everybody was right on that. And final question. Whoops, wrong way. Final question. What kind of magnetism is always repulsive? Okay, this one not as good on. It is the diamagnetism that is always repulsive. Paramagnetism is weak but attractive. Now we have 3 minutes left, and I want to get to the first type of actual calculational problem we can do. So what is the first kind of problem? It's a little surprising. If you have an electron and it's in a magnetic field, the force due to magnetism is 0. The electric charge is not what interacts with the magnetic field if it's stationary. Now it's related to charge. So that's why I said if it's stationary. If it's moving, there will be a force. So if it's moving, so if I have this electron moving like this, then the equation for force is going to be force is equal to Q V vector cross B vector. It's a cross product. We did cross products last semester. I spent time working on the right-hand rule for the cross product, and I was really careful to say, like on the test where we had a question about the cross product, I said, if A equals B cross C, because cross products appear multiple places in physics. And here's one where we can't get away from the right-hand rule. So the force, if it's cross product, we know that we're multiplying which parts of the two vectors? The perpendicular parts. Cross product is multiplying the perpendicular parts, and the result of a cross product is a vector that's perpendicular to both of the original pieces. So with my cross product, in my picture up there, the velocity is down, and the magnetic field is pointing to your right. And so what direction is perpendicular to both down and right? Perpendicular to there and there. What direction is perpendicular to my two arms? Either coming out or going in. And that's where we have to use our right-hand rule to determine which one. V cross B, if I look at that, my V is down, my V is that way, so index finger down, middle finger in the direction of B. My thumb comes out of my chest toward you. But then it's got a negative charge. So it's negative in that direction, hence it's that direction. Okay, now we are out of time. I'll see you Friday.